Welcome back to the AI Canon. In today's explainer, we're going to perform an academic exorcism of sorts. We are going to carefully dispel the ghost in the machine. We'll be investigating the oldest, and honestly, perhaps the most profound debate in computer science, the fundamental difference between computer simulation and true sentience.
And it's a debate that has forced computer science and philosophy into this shared arena of inquiry for over 70 years now. The core question is this: is cognition merely a matter of executing the correct computational processes, or does it require an internal, conscious grasp of meaning? Today, we'll examine the historical roots of that question, and we'll discuss why the answer has urgent, practical implications for exactly how we govern modern artificial intelligence.
Today's explainer follows a straightforward dialectical structure. We'll start with the anthropomorphism trap, analyze Alan Turing's imitation game, and then look at its primary counterargument, John Searle's Chinese room. From there, we'll synthesize the divide between syntax and semantics, apply it to modern probability engines, and wrap up with the syllabus.
Let's get right into Section 1, the anthropomorphism trap, the flaw of human social cognition.
Before we look at the machines themselves, we really need to look at ourselves, specifically our evolutionary tendency to project intention onto non-living systems. You see, digital anthropomorphism isn't just a failure of rationality. It's actually a manifestation of human social cognition. Research into the CASA paradigm, that's computers are social actors, has firmly established that humans inherently apply social expectations to computers. When conversational software uses natural language proficiency, it immediately activates our social brain mechanisms. We project empathy, intention, and moral agency onto what is essentially just simple pattern-matching dialogue. And what's deeply ironic here is that this ELIZA effect leads not just the general public, but even highly experienced developers to falsely treat AI systems as independent decision-makers rather than the probabilistic tools they actually are.
Which brings us to a crucial warning issued by the computer scientist Edgar W. Dijkstra back in 1985. He wrote, "A more serious byproduct of the tendency to talk about machines in anthropomorphic terms is the companion phenomenon of talking about people in mechanistic terminology. This represents a long-recognized intellectual danger. When we carelessly use words like understands, decides, or hallucinates to describe software, we not only distort the limits of what a program can do, but we reduce the profound complexity of human cognition, your cognition, to mere mechanical computation."
Moving on to Section 2, Turing's imitation game, behavioral functionalism.
To understand how we arrived at this linguistic confusion in the first place, we have to step back to the year 1950 to examine the foundational text of computational theory. That year, the British mathematician Alan Turing published Computing Machinery and Intelligence. Turing deliberately sought to bypass the question, can machines think, because he viewed terms like thinking as highly subjective and culturally loaded. His work laid the pragmatic foundation for a theory that was later developed in the 1960s by Hilary Putnam, known as functionalism. Functionalism essentially argues that we should de-emphasize the actual structure of internal processes. Instead, intelligence is attributed to a system if its behavioral functions and outputs perfectly match those of an intelligent entity.
To operationalize this theory, Turing proposed his famous imitation game. The mechanics involve a trio. You have a man trying to deceive, a woman trying to assist, and an isolated interrogator who is trying to determine who is who, strictly via typewritten text. Turing's theoretical substitution here was beautifully simple. He asked, what happens when a machine takes the part of the deceiving man? If the interrogator cannot reliably distinguish the machine's text from a human's text, Turing argued that we must pragmatically concede that the machine possesses intelligent behavior.
And that takes us to Section 3, Searle's Chinese room, the limits of symbol manipulation. So, Turing's behavioral pragmatism quickly became the dominant paradigm in computer science, but it faced a rigorous philosophical antithesis. 30 years later, in 1980, the philosopher John Searle published a direct challenge to the functionalist view. He posed one central question: does passing the Turing test equal true understanding? Searle argued that it absolutely does not. He completely challenged the deeply held notion that intelligent behavior or observable fluency equates to conscious cognition, and to prove his point, he designed a very elegant thought experiment. Consider the Chinese room. Imagine an individual who speaks only English, locked inside a room. Through a slot in the door, they receive pieces of paper with Chinese symbols on them. Inside the room is a massive, comprehensive English rulebook. This rulebook dictates precisely how to match the incoming symbols with other Chinese symbols and how to pass those new symbols back out of the room. Now, to an observer on the outside, the room is answering questions in fluent Chinese. It passes the Turing test with flying colors. But the person inside doesn't understand a single word of Chinese. They're merely manipulating symbols according to formal instructions. Searle's point is definitive here. A computer program operates exactly like the person in that room.
Which brings us to Section 4, Syntax versus Semantics, the core philosophical divide.
This is where we synthesize these opposing frameworks to isolate the exact boundary between computing and comprehension. Searle's Chinese room cleanly separates two distinct concepts: syntax and semantics. Syntax refers strictly to formal mathematical rules, the physical shapes of symbols, and the algorithmic manipulation of those shapes. That is the domain of computational processes. Semantics, on the other hand, is the actual meaning. It's the internal comprehension and the intentionality that connects a symbol to a real-world reference. Searle's definitive conclusion is that syntax alone is not sufficient for, nor constitutive of, semantics. Simply moving symbols correctly is not the same thing as understanding what they mean.
Let's apply this in Section 5, the probability engine, applying philosophy to modern LLMs.
We really need to bring this philosophical history into the present day to analyze the large language models that are driving contemporary software architecture. When we look at the architecture of a modern neural network, mapping data points from the input layer through the hidden layers all the way to an output layer, we are looking at the ultimate manifestation of the Chinese room. These models map inputs to outputs based purely on syntactic mathematical weights. There is no biological structure there that is causally capable of producing perception or understanding. The system is executing a highly complex, multidimensional rulebook, but it remains fundamentally devoid of semantic comprehension.
And this reality is perfectly captured by the term stochastic parrot, which was coined by Dr. Emily Bender and her colleagues. Large language models are, at their core, probability engines. They generate plausible, fluent text based on statistical probabilities derived from vast training datasets. They possess no actual intent, no sentience, and certainly no real-world comprehension of the output they produce. They are structurally incapable of having beliefs or desires. So categorizing them as probability engines rather than conscious entities is not just a philosophical preference, it is a strict technical necessity.
Understanding this technical necessity yields some crucial, practical mitigations for software engineers and technology leaders today. First, we have to combat the confidence heuristic. Because probability engines prioritize fluency over truth, developers cannot simply trust an assertive tone. They have to actively verify probabilistic outputs.
Exactly. And secondly, it closes the responsibility gap. When AI is framed as an independent decision-maker, it allows organizations to engage in moral scapegoating. As outlined in recent legal frameworks, AI is simply an instrument. The deployers and developers remain entirely accountable for its outputs.
That accountability also extends to recognizing social engineering risks. Interfaces designed to elicit emotional dependency routinely trick users into exposing proprietary data. We must actively avoid building those patterns.
Right. Which means organizations must enforce trust calibration, utilizing strict counter-anthropomorphism exercises to ensure epistemic vigilance remains high across the board.
Finally, Section 6, Course Syllabus and Outro.
This concludes our dialectical analysis of the boundary between simulation and sentience. By understanding the mechanical reality of probability engines, we can reject the dangers of digital anthropomorphism and build safer, significantly more accountable systems. To pursue this inquiry further and view the complete syllabus, which details the foundational papers by Turing, Putnam, and Searle, please visit bestai.org/canon/imitation game. We leave you with this final thought. If our machines are merely mimicking sentience, how long until we begin mimicking the machines?